Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today, we are going to discuss about a module, Linear Harmonic Oscillator, Operator Method, under the paper Quantum Mechanics 1. After studying this module, you shall be able to Number 1. Know the important role the study of harmonic oscillator plays in the diverse areas in physics. 2. Learn some general properties from the given form of the harmonic oscillator potential. Number 3. Learn to write the Hamiltonian in the operator form, that is, the raising and the lowering operators, and hence to be able to deduce the expressions for the energy spectrum. Then you will also learn to deduce the expression for the energy eigenstates of the Hamiltonian. And finally, you will be able to show how this representation of the states can be expressed in terms of the Hermite polynomials. The study of the quantum mechanical properties of a linear harmonic oscillator assumes its importance from the fact that it provides the basis to analyze a wide variety of physical phenomena, such as the vibrations of atoms of a molecule about their equilibrium positions, the oscillations of atoms or ions of a crystalline lattice, etc. In the first module, we saw that it was the study of the behavior of these oscillators at thermal equilibrium, that is, blackbody radiation, which led Planck to introduce the hypothesis of quantization of energy. Whenever one has to study the behavior of a physical system in the neighborhood of a stable equilibrium position, one has to deal with the equations which, in the limit of small oscillations, are those of a harmonic oscillator that you have already studied in your undergraduate course on quantum mechanics. And you must have studied the problem of the linear harmonic oscillator by solving the time-independent Schrodinger's second-order differential equation. Dirac's operator method for the oscillator. In quantum mechanics, the classical quantities x and p, that is, the position and the momentum, are replaced by the corresponding operators in terms of which the Hamiltonian operator of the system is expressed. We have already studied that the Hamiltonian of a linear harmonic oscillator in quantum mechanics is expressed as operator H is equal to momentum operator square upon twice mass plus half times mass into square of the angular frequency into square of the position operator. And for the time-independent Hamiltonian, we have the eigenvalue equation, operator H acting on the ket vector phi is equal to the energy eigenvalue times the ket vector phi. Written explicitly in the position representation, that is in the ket vector for the position representation, this has the form within brackets minus h cross square by 2m double differential with respect to the position x plus half m omega square operator x square whole times phi x is equal to e phi x. Here h cross is the is h by 2 pi, where h is the Planck's constant, m is the mass, omega is the angular frequency, operator x is the position operator, phi x is the wave function or the eigenvector, and E gives the energy eigenvalues corresponding to the eigenvector phi x. For the Hamiltonian operator, this is the second order differential equation which we have studied and solved to get the solutions for the eigenvalues and eigenfunctions of the oscillator. We have studied in the preceding module that there are many representations connected by unitary transformations, in which the wave functions and operators can appear in quantum mechanics. In the Dirac's formulation of quantum theory, the central role is played by the commutation relations between linear Hermitian operators corresponding to the dynamical variables. Here, we shall use Dirac's method, which essentially consists in finding suitable operators with which one can generate all the eigenvectors of the Hamiltonian without making reference to any particular representation, raising and lowering operators. Now, corresponding to the Hamiltonian given above, we can introduce the operator A plus is equal to 1 upon under root 2m h cross omega whole times within brackets m omega operator x minus iota times operator p, and the other operator is defined as operator A minus is equal to 1 upon under root twice times mass times h cross times omega whole multiplied by within brackets m omega operator x plus iota times operator p. So the operators A plus and A minus are basically the raising and the lowering operators. That is, when they act on any eigenvector, they either increase the number by 1 or decrease the number by 1 respectively. Here, since the position operator x and the momentum operator p are Hermitian operators, therefore the raising and the lowering operators, that is A plus and A minus, are adjoint of each other. In other words, we can say that the operator A plus is equal to operator A minus dagger, and similarly the operator A minus is equal to operator A plus dagger. Now, using the commutation relation between the position and the momentum operator, we have commutation relation of the position and momentum operator gives us iota times h cross, where h cross is equal to h by 2 pi and h is the Planck's constant. Thus, it is now easy to verify that the raising and lowering operators A plus and A minus satisfy the commutation relation of raising operator A plus with the lowering operator A minus gives us the identity matrix or the unit matrix. Writing the operators for the position and momentum, that is operator x and operator p, in terms of the raising and lowering operators, that is A plus and A minus respectively, we get the value of the position operator as operator x is equal to under root h cross by twice times mass times angular frequency whole multiplied by the raising operator plus the lowering operator. Similarly, the momentum operator, operator P, is given as 1 upon twice iota times whole times under root twice into mass into h cross into the angular frequency times within brackets the lowering operator A minus minus the raising operator A plus. Number operator. We have seen that the position operator x and the momentum operator p can be written in terms of the raising operator A plus and the lowering operator A minus. And using these expressions for the position and the momentum operator, we can substitute these in the equation for the Hamiltonian, and from that one can show that the Hamiltonian operator turns out to be equal to h cross omega by 2 whole times within bracket the lowering operator A minus, the raising operator A plus, plus the raising operator A plus times the lowering operator A minus. And this can then be simplified to give us the relation h cross omega whole times within the brackets the lowering operator A minus times the raising operator A plus minus half. And then substituting for the value of the number operator, that is, we get number operator as the raising operator A plus times the lowering operator A minus, and the Hamiltonian operator is then given by h cross omega whole times within brackets the number operator n plus half bracket closed. So in this manner, expressing the Hamiltonian in different forms, we make use of the commutation relations. Here, it is very important to note that the number operator n dagger is equal to the lowering operator A minus dagger times the raising operator A plus dagger, and this is equal to the raising operator A plus times the lowering operator A minus, and which turns out to be equal to the number operator. Thus, we can show that the number operator n is Hermitian, which means that the number operator n turns out to be equal to its complex conjugate or the adjoint. Now, by relating the Hamiltonian to the number operator n, the problem of determining the eigenvector and the eigenvalue of the Hamiltonian is essentially reduced to finding the eigenvalue and eigenvector of the number operator. Action of the raising and lowering operators, operator A plus and A minus, on the eigenvector of operator n, that is the number operator. Now, calculating the commutator of the number operator n with the raising operator A plus and the lowering operator A minus, we find that the commutation relation or the commutator of the number operator with the lowering operator A minus is equal to commutation relation of the raising into the lowering operator, that is A plus, A minus, and the lowering operator A minus, since the number operator is given as the product of the raising operator times the lowering operator. That is, first we have the raising operator followed by the lowering operator. And this, if we further solve the commutation relation, turns out to be equal to raising operator times the commutation relation between lowering operator and the lowering operator plus the commutation relation between the raising operator and the lowering operator whole times the lowering operator. And this finally gives us the result that the commutation relation or the commutator of the number operator with the lowering operator turns out to be equal to minus the lowering operator A minus. Similarly, the commutator of the number operator with the raising operator a plus is equal to the commutator of a plus a minus, that is the raising operator, lowering operator, with the raising operator a plus. And this, when we solve it, turns out to be equal to the raising operator times the commutator between the lowering operator a minus and the raising operator a plus the commutator of the raising operator with itself whole times the lowering operator. And this, when solved, gives us finally that the commutator of the number operator with the raising operator is simply equal to the raising operator. Now, let the ket vector phi n represent the eigenvector of the number operator, so that number operator acting on the ket vector phi n or the eigenvector gives us n times the eigenvector or the ket vector phi n. Now, using the equation for the commutator between the number operator and the lowering operator, we have, and substituting it over here, we get the commutator of the number operator and the lowering operator acting on the eigenvector phi n is equal to minus lowering operator a minus times the eigenvector phi n. Now, if we solve the left-hand side of the above equation, we see that it turns out to be equal to, after rearrangement of terms, that the number operator times the lowering operator acting on the eigenvector phi n is equal to the lowering operator acting on the number operator acting on the eigenvector phi n minus the lowering operator a minus acting on the eigenvector phi n. And this in turn comes out to be equal to n minus 1 whole within the bracket times the lowering operator a minus acting on the eigenvector phi n. This relation shows that the operation of the lowering operator a minus on the eigenvector phi n is actually an eigenvector of the number operator with the eigenvalue corresponding to n minus 1. Similarly, one can show that the eigenvector of the square of the lowering operator on the eigenvector phi n, that is, if the lowering operator acts twice on the eigenvector phi n, then the corresponding eigenvalue turns out to be n minus 2. Eigenvalues of the lowering operator to the power s, that is, if the lowering operator acts on an eigenvector s times. Now, from the relation that we have derived for the lowering operator acting on the eigenvector, we can generalize that relation to a situation where the lowering operator is acting on the eigenvector, let's say r times, where r is some number which is less than n. Then the lowering operator a minus acting r times on the eigenvector phi n of the number operator gives the eigenvalue n minus r. Here we need to note that the eigenvalue n corresponding to the number operator n is given by the average value of the number operator or the norm of the number operator with the eigenvectors phi n, that is, bra vector phi n, number operator, ket vector phi n. And now if we replace the number operator with its corresponding value in terms of the raising and the lowering operator, then the equation that we get is bra vector phi n, the raising operator a plus, the lowering operator a minus acting on ket vector phi n, and this gives us the square of the norm of the lowering operator a minus acting on the eigenvector phi n, which should be greater than or equal to 0. The reason why this is so is that the norm of a vector is always positive definite. So the lowering operator acting on the eigenvector phi n must be non-negative. What this actually means is that supposing if we have a series of operations, that is, if we have a series where we start with the eigenvector phi n, then the lowering operator acting once on the eigenvector phi n, then the lowering vector a minus acting twice on the eigenvector phi n, and so on till the lowering operator a minus acting r times on the eigenvector phi n, and so on, then we see that this series must terminate, as otherwise it would lead to a state for which the operator would give the eigenvalue which is negative. As a general property of a linear harmonic oscillator having a potential V as a function of x is greater than V naught, which is some threshold potential or the initial potential, we have also noted in the earlier subsections that for such cases the eigenvalues are always positive. Thus, the last term in the series generate the state phi naught, that is the ground state or the lowest state of the eigenvector, such that the lowering operator a minus acting on this lowest or the ground state eigenvector phi naught is equal to 0. What this actually means is that the above series must have eigenvalues corresponding to n, n minus 1, n minus 2, and so on till we finally reach 0 for the lowering operator acting n times on the eigenvector phi n. Similarly, we can also derive the relation involving the commutator or the commutation relation between the number operator and the raising operator. And this turns out to be that the commutator of the number operator and the raising operator acting on the eigenvector phi n is the raising operator a plus acting on the eigenvector phi n. Further, one can also show that the number operator acting on the raising operator a plus acting on the eigenvector phi n is equal to the raising operator acting on the number operator acting on the eigenvector phi n plus the raising operator a plus acting on the eigenvector phi n. And this turns out to be equal to within brackets n plus 1 whole times the raising operator a plus acting on the eigenvector phi n. Action of raising and lowering operators. From our previous discussion, we can say in general that the number operator acting on the raising operator acting r times on the eigenvector phi n gives us within brackets n plus r times the raising operator a plus acting r times on the eigenvector phi n. That is, n plus r is the eigenvalue corresponding to the eigenvector phi n when the number operator and the raising operator acting r times acts on the eigenvector phi n. As a result, we get the series corresponding to the eigenvalues n plus 1, n plus 2, and so on, n plus r, and further continues, where the eigenvalue n plus r corresponds to the number operator acting on the raising operator which acts r times on the eigenvector phi n. Thus, the eigenvalue spectrum of the operator n, that is the number operator, ranges from 0, 1, 2, and so on till infinity. For the Hamiltonian operator h, we have that this can be given in terms of the number operator as operator h is equal to within brackets number operator n plus half whole times h cross omega, where h cross is equal to h by 2 pi, and h is the Planck's constant and omega is the angular frequency, operating on the eigenvector phi n. Thus, from the above relation, we have that if the Hamiltonian operator acts on the eigenvector phi n, we get finally h cross omega times within brackets the number operator plus half acting on the eigenvector phi n, and this in turn gives us h cross omega times within brackets n plus half whole times the eigenvector phi n, and this is equal to the energy eigenvalue times the eigenvector phi n, where the energy eigenvalue of the Hamiltonian operator is given by En is equal to n plus half within brackets whole times h cross omega, where n can vary from 0, 1, 2, 3 and so on till infinity. Clearly, by operating the lowering operator A minus on the eigenvector phi n, the eigenstate of the Hamiltonian operator H, we get that the corresponding eigenvalue changes to En minus 1, and this is given by En minus 1 is equal to within brackets n plus half whole times h cross omega minus h cross omega. So, which in turn gives us that the energy eigenvalue En minus 1 corresponding to the lowering operator acting on the eigenvector phi n is equal to within brackets n minus half whole times h cross omega. Thus, we can see that the number gets lowered, that is the value of n gets lowered by 1. Similarly, if one operates the raising operator, the eigenvalue is increased by 1, and this is the reason why the operator A plus is called the raising operator, while the operator A minus is called the lowering operator. Eigenstates of the Hamiltonian. Now, if we want to find out the eigenstates of the Hamiltonian, we start with the eigenvector phi naught with n equal to 0, which satisfies the property lowering operator A minus acting on the eigenvector phi naught gives us 0. Assuming it is normalized, the next state corresponding to n equal to 1 is then obtained by writing eigenvector phi 1 is equal to C1 times the raising operator A plus eigenvector phi naught. To determine the constant C1, we normalize the eigenvector phi 1. So, bra vector phi 1, ket vector phi 1 is equal to the square of the modulus of C1 times the expectation value of the eigenvector phi naught with the lowering operator A minus and the raising operator A plus, and this gives us the square of the modulus of C1 times bra vector phi naught within brackets raising operator A plus, lowering operator A minus plus 1 acting on ket vector phi naught. Since the ket vector phi naught is normalized and the number operator n is equal to the raising operator A plus, the lowering operator A minus, and has 0 eigenvalue on the ground state or the lowest state eigenvector phi naught, we can write the bra vector phi 1, ket vector phi 1 is equal to square of the modulus of C1, which turns out to be equal to 1. Now, choosing the phase of the ket vector phi 1 relative to the ket vector phi naught to be such that C1 is real and positive, we set C1 equal to 1. As a result, the ket vector phi1 can now be represented in terms of the ket vector phi0 as ket vector phi1 is equal to the raising operator A plus acting on the ket vector phi0. And proceeding in the same way, we get for the ket vectors phi2, phi3 and so on, where ket vector phi2 is given by 1 upon under root 2 times the raising operator A plus acting on the ket vector phi1, and this can then be written as 1 upon under root whole times the raising operator A plus acting twice on the ket vector phi0. Similarly, we can then generalize this result to n, and extending it to n equal to n, we write Cn is equal to 1 upon under root n matrix representation of the operators. Now, we can represent the state eigenvector phi n in terms of its ground state or the lowest state given by the eigenvector phi naught, and we can write the eigenvector phi n as equal to 1 upon under root n times the raising operator A plus acting on the eigenvector phi n minus 1, and this can further be written as equal to 1 upon under root n times 1 upon under root n minus 1 whole times the raising operator A plus acting twice on the eigenvector phi n minus 2, and then we can go on adding to the series, that is, we can go on decreasing the value of the n by 1 every time as we go on increasing the number of times the raising operator acts on the eigenvector phi n minus the number of times that the raising vector is operating. And thus, in this manner, finally, we can get the relation that the eigenvector phi n is equal to 1 upon under root n times 1 upon under root n minus 1 times so on times 1 upon under root 2 whole times the raising operator A plus acting n times on the ground state or the lowest state eigenvector phi naught. And this can be written in a concise form as 1 upon under root n factorial whole times the raising operator A plus acting n times on the eigenvector phi naught, so that the expectation value of the eigenvector phi n with respect to the lowering operator A minus, that is bra vector phi n prime lowering operator A minus ket vector phi n is given as under root n times delta operator n prime comma n minus 1. That is, if n prime is equal to n minus 1, then the delta operator gives 1. Otherwise, it gives 0 value for all n prime not equal to n minus 1. In a similar way, we can also write that the raising operator A plus acting on phi n gives us under root n plus 1 whole times the eigenvector phi n plus 1. And the expectation value of the eigenvector phi n is given as bra vector phi n prime, the raising operator A plus ket vector phi n is equal to under root n plus 1 delta operator n prime comma n plus 1, where the delta operator gives the value of 1 for n prime equal to n plus 1, and for all other n prime not equal to n plus 1, it returns the value 0. Wave functions of stationary states. Now, using the definition of the lowering operator A minus, we can write that 1 upon under root twice times the mass times h cross times the angular frequency omega whole multiplied by within brackets m omega times the position operator x plus iota times the momentum operator p whole times the eigenvector phi naught is equal to 0. Or in other words, what we have already discussed earlier, that the lowering operator acting on the lowest or the ground state eigenvector phi naught will give us 0. In the complete basis representation of the position eigenvector x, that is the ket vector x, we have phi naught x as given by bra vector x, ket vector phi naught. So the equation that we get for this is 1 upon under root twice times mass times h cross times the angular frequency whole times within brackets m omega x plus h cross the derivative with respect to the position x whole times the ground state function phi naught x, and this turns out to be equal to 0. The solution for this equation is given by phi naught x is equal to n naught times the exponential of within brackets minus m omega by twice h cross whole times x square, and this can further be written as n naught times exponential to the power minus alpha square x square by 2, where alpha is given by under root m omega by h cross and n naught is the normalization constant, which is given by n naught is equal to alpha upon under root pi whole to the power half, and this can further be written as m omega by pi h cross whole to the power 1 by 4. Similarly, the other eigenfunctions are obtained by the raising operator a plus, and we can write that phi nx is equal to bra vector x ket vector phi n, and this is equal to 1 upon under root n factorial whole times bra vector x, the raising operator a plus acting n times on the ket vector phi naught, and this can further be written as 1 upon under root n factorial times 1 upon under root 2 to the power n whole times within bracket under root m omega by h cross whole times x minus under root h cross by m omega whole times the derivative with respect to position x, this whole within bracket raised to the power n times phi naught x. Identifying eigenfunctions with Hermite polynomials. Now, we can use the representation of the Hermite polynomials, which is given by hn as a function of rho is equal to minus 1 whole to the power n exponential to the power rho square, the nth derivative with respect to rho of exponential to the power minus rho square, and this Hermite's polynomial can then be further written as exponential to the power rho square by 2 whole times within brackets rho minus derivative with respect to rho whole to the power n whole times exponential to the power minus rho square by 2. Using this representation of the Hermite's polynomial and defining the variable rho as alpha x, which is equal to under root m omega by h cross whole times x, and then using this relation, seeing that the derivative of any quantity with respect to the variable rho, that is the derivative with respect to rho d by d rho, turns out to be equal to under root h cross by m omega whole times the derivative with respect to x, that is d by dx. After we have derived all these relations, we can now write the ground state eigenvector or the eigenfunction phi naught as a function of the variable rho as given by n naught times exponential to the power minus rho square by 2, and this can further be written by replacing rho with its corresponding value that we have defined above as within brackets alpha upon under root pi whole times exponential to the power minus rho square by 2, and we can re-express the nth eigenfunction, that is the eigenfunction phi n as a function of the variable rho as given by within brackets alpha upon under root pi times 2 to the power n times n factorial whole to the power half exponential to the power minus rho square by 2 whole times the Hermite polynomial h n rho. So students, let us now summarize what we have learnt in this module. So, after studying this module, you would be able to explain the important role the study of harmonic oscillator plays in the diverse areas of physics. You would have also learnt some of the general properties from the given form of the harmonic oscillator potential. Further, you would have also learnt how to write the Hamiltonian in the operator form, that is, in terms of the raising and the lowering operators, and to deduce the expression for the energy spectrum. Also, you would have learnt to deduce the expression for the energy eigenstates of the Hamiltonian. And finally, you would have learnt how to show this representation of the states can be expressed in terms of the Hermite polynomials. Thank you.